Okay, before Amanda takes over, just a little bit of background. Again, a reminder, we wanted to give you all hands-on experience with actually simulating Xenobots, then wrapping an AI around those simulated Xenobots, and then usually Doug or Pi or Halle would actually manufacture some in vitro Xenobots. We're going to skip that step and you're going to get to see some in vitro Xenobots tomorrow. So what Amanda's going to do is walk you through the first of this 3-part tutorial series in which you're going to create a simulation of Xenobots. Okay. I am going to have to step out for a couple of hours. I will be back at 4 o'clock for the collective writing assignment. Mike will be in charge while I'm away. Don't burn the building down, Mike. Please. Okay. Amanda Bertschinger is a doctoral candidate in my lab, and she's a rising star in the very demanding field of symbolic regression. We are not going to talk about symbolic regression today. Amanda will tell you it's super hard. Symbolic regression is about teaching AI to compress raw data into understandable equations. And there is a connection between Xenobots and symbolic regression. If you're interested in any of those keywords I just mentioned, please be sure to ask Amanda about it. That's not what she's going to be doing today. She is going to be allowing you in the cloud to simulate Xenobots, and I will see all of you at 4 o'clock. Amanda.
Great. Thank you. Hello, everyone. Hopefully everyone's good if I say. Welcome. Thanks for coming to the demo. Over the next hour-ish, this demo is aimed just to show you how we create a virtual sandbox and simulate Xenobots in that virtual sandbox. The goal here is to get you more familiar with simulation, so we would love for you guys to get your hands dirty, well, as dirty as your keyboards are, I suppose, and just understand the technology we use better. The goal with that is if you guys understand the technology we use better, you'll be able to better advise us on what we're doing and what we could do better. So that's kind of our goal here. So earlier in the presentation, we've learned about Xenobots and some of the exciting experiments done with Xenobots already. However, and this was even referenced by Thomas, there's only about 5 people in the world that can currently create Xenobots. About 3 of them are here with us in this room today, and the other 2 are unfortunately not with us. But that doesn't leave a lot of ability to create Xenobots for experiments. And ultimately, unsurprisingly for those who have done any scientific research that requires, especially biology experiments, you often need a lot of experimentation to learn how to get Xenobots to act in the way we actually want them to, so that we can have them do for some purpose and not just moving around in a dish. As cool as that is, love that they move around in a dish right now. So, in order to be able to do experiments on them, we make use of simulation. We simulate Xenobots in a virtual environment on our computers because that saves us from having to have the 5 experts that we have available actually create physical Xenobots for us. That is not to say that we do not need actual experiments with biological Xenobots. We definitely need those. Simulation will never be as good as biology, the actual biological Xenobots, but we can get close. We can get good enough simulation to be able to sort of explain some of the behaviors that we see. With that spiel done, if everyone can get out either a phone or a computer and go ahead and direct your web browser to this address up here, bit.ly.
How do we get on the web, sorry?
Oh, are you not connected to the internet?
No.
Krishna, can you? I believe it's UVM guest.
UVM guest, yeah. Okay.
And you could enter your phone number, you could get a PIN, and then log in.
Registered by
people are on
right?
Yeah,
or
that's
need,
right.
or need this help? Everybody.
I don't need help.
Okay. If you need help with the internet, keep your hands up, and Krishna and I will come to you.
Okay.
For those who are on the internet, and I'll leave this up on screen.
So all I see is a bunch of Java shit.
Yes.
What should I see?
That you should, once you go to that web address, you should see a WCDO IPython notebook in Google Colab.
I don't believe in those.
What was the address? What's the address?
The address is bit.ly/WCDO.
Did you get it? I don't think we're getting the SMS on international numbers.
Oh,
Yeah. It's not.
you could enter my number.
Oh yeah. Okay.
It's just to get
No, definitely not.
go back.
Yeah.
This is the number.
Enter the. So sorry. Yes. Okay. Yes.
Do I need to zoom in?
929
353
353 9.
00 /
Okay. So we go.
Amanda, if you could zoom in a little bit.
Yeah.
Oh, yeah, there we go. It's WCDO25. Ah.
960
6
960.
960.
And it should take you to a Google Colab folder that says wcdo.inv, day one simulation, and then have some
9009.
cells that we're gonna run. But I'm gonna go back to the web address.
And so we're going to
05 B2.
Okay, so beats.
Yep. Alright, can I get a show of hands on how many people were able to get to the notebook? Okay, great. We have a majority, so we're gonna move on, but if anybody still needs help getting to the notebook, then just flag down Christian or Thomas and they'll be able to help you, okay?
Yes, good.
Great. Alright, so once we're there, so that we're all, the glory of technology is that we can all access this page together. Unfortunately, if we all try to run it together, then we're going to interfere with each other. So we're going to go under File, Open File, and then Save a Copy in Drive. This does require you to have a Google Drive account.
Can you show the bit.ly again?
Yeah. Sorry, we're slow. We're from Europe.
All good, all good.
Being in the first row doesn't help.
Gee, you guys are such troublemakers.
Alright, Krishna, do you know it?
It's WC.
Great. Krishna knows it.
You're missing.
Has everybody managed to make a copy? It's File and then make Save Copy in Drive.
You did?
Save as
So
copy.
this is such a case sensitive.
Oh,
Yeah, it's case sensitive.
Yeah.
Yeah.
Yeah, now I realize.
Now
Yeah.
we
You can use a low case framework.
I don't know where my bag is.
Thank you.
sorry, save as copy.
File.
Yeah, go with my medication.
I think I've done it already.
It should say copy.
Shows on who's that.
Alright, has everybody managed to make a copy of the WCDO notebook? Hands up if you have. You go to File and then Save a Copy in Drive. Okay. So, the first thing that we need to do is we're going to need to create a virtual sandbox to simulate our Xenobots in. And so to set up this virtual sandbox, the first thing we're going to need to do is run this first line of code. It's just installing a Git repo and a bunch of stuff that we need to do that and setting up this virtual sandbox. So just click this nice play button in that step 1 and it should run for a little while.
File copy.
Which language is it in?
It's in Python.
Okay.
But Python should run on the Google Colab folder. And then when it's done running, you'll see this green check mark to the side of that first code, step 1, and it'll have, it's fine if it doesn't say 21 seconds, that's just how long it took to run on mine. But just when you get that, if I could have a show of hands, who's been able to execute that? Great. You just unknowingly created a virtual sandbox with some, but it's currently empty. There's nothing in it. So we need to create some cells for our virtual sandbox, for our playground. Yep.
Can you maybe say a few words about the concept of like what parameters are in this virtual sandbox?
Yeah. So at the moment, we will see it in a second, an actual visual representation of it. But at the moment, what we've done is we have created a world with a floor and gravity.
Great, thank you.
And that's all behind the scenes in that Git repo, running that, just executed all of that. But that we've just set up the most basic thing we can, which is just an empty world with a floor that you can collide with, an object can collide with, and gravity implemented. Earth gravity at -9.8. So let's add something to our sandbox so that we actually have something. Run that step 2 cell. This is, we call it sprinkle cells because we are sprinkling some cells into our virtual sandbox so that we can play with those. That should run pretty quickly. Does everyone have that green check mark next to step 2? Great. Now, let's actually see what we've done. We actually want to see the sandbox that we've created and the cells that we've created in it. So go ahead and run that step 3 cell by clicking on that play button. And this will actually download a video to your device. So if you're on a phone, go to your gallery or photos. If you're on a laptop, should be able to pop up from your downloads. Of course, it opened it on the wrong screen for me.
Nice.
Just play those two.
Yeah.
And you should get something that looks like this. A video that just has some cells in it. Just some static cells in a world. And I guess this is sort of the very basic default of what we start with when we start with these simulations. Because now that we have this simulated world with some cells in it, we can finally start to make them act like our actual Xenobot cells do. Has everyone been able to get to this step? Great. So the next thing we're going to do is we're going to add mobility to the cells because the cells that we've seen in videos, Xenobot videos we see, they're not static, they move. So we're just going to run step 4. This is sort of where the simulation falls apart, that no matter how sophisticated of a model and simulation we make, it's not biology. It's never going to be a one-to-one recreation of biology. So we need to add in more details to our simulator in order to better replicate reality. And to do this, for this step, we are just adding motility. Again, that should have downloaded another video folder. And if you open that, you should now see cells moving a little bit. So we've just added a little bit of motion and ability for our cells to wiggle and move around. So now we have a okay environment in which we have some cells wiggling around, and now we can do some experiments on them. So first of all, at this stage, and hopefully everyone's seeing this video, great. We have a lot of individual cells that aren't moving together. They're all moving randomly. But Xenobots, the Xenobots that we've seen, they are collectives of cells that are grouped and move together. So we want to add some grouping capability into our simulation, into our cells, so that they group together. So go ahead and run step 5. Again, this should download a video when it is done running. And from this video, we should be able to see cells actually coming together and starting to group together, being pulled in. Does everyone see that? Great. So, at this moment, not in this demo, but at this moment in our research, we have two ways that we can make xenobots. One of them is several members of this room can do it, like Pi, and Pi, if I can ask you to speak just really quickly, why do we want to group cells like we are showing on screen right now? Like, why is it important for us to shove them together?
Well, because then you're going to get structural formation and the cilia development with which they move. I mean, yes, these individual cells will move, but not very much. They will just wiggle around in their own place.
So, our two methods right now to be able to get these cells to move together in the real world are Pi, Doug, Cam now has some experience with that, and a few other people, Sam and so forth. But again, very difficult for our experts to be able to do it at scale. And the other way that we have found to make cells move is to apply an electronic field to it. For more information on how that works, please reference Doug and Mike. That was not my research. I don't do anything on the biology side of things. I'm just here to show you how to do a simulation. So for now, just trust me when I say that applying an external electric field causes cells to move. That is what we're going to do next. We're going to create an electric field for the cells to move in and see how that affects the cells in our simulation. So go ahead and run step 6. For now, you can ignore what all of this means. It'll be more relevant later. There's questions about it, there's more math, but basically running step 6 is just going to create an electric field. And when you run it with the all the values here being 0, you'll just see an electric field that has no directionality. So you go ahead and just try changing one of those values. I'm going to change the first one to 1. And when you rerun that cell, now you'll see that there are arrows, and this is actually our electric field that we had just created. Feel free to change as many of the numbers in there as you want to get something that looks like mine. Just make that first number 1. Is everyone seeing an electric field?
Amanda, what you say we're seeing an electric field? What are the dots? Like, what is this thing we're looking at?
The arrows are showing the direction of current in the electric field that we just created.
And the dots are.
The dots are arrows.
That's the.
How
What?
does this relate to our sandbox?
Yes, we're about to apply it to our sandbox. We have not applied it yet. This is just the electric field that we will be applying. So if everyone's got an electric field, you can go ahead and run step 7 to actually apply that electric field to our virtual sandbox. Again, this will download a video, and we will be able to see cells moving around by the electric field and being affected by the field itself. So now we'll see, instead of them being a group, they just move in the direction of the electric field. Hopefully everyone's seeing that. So, if everyone's seeing those, the next step, is closing my entire everything. There we go. The next step, as I said, there's several things. There are several fields here, and as you change variables from 0 to 1, or really anything in between, you can create different electric fields of different orientations, and then you can rerun those. And then here in step 7, if you just, under the num seconds variable, you can increase that to see cells moving more over time and more of theirs. So at this point, I just release up to you and see if any of you can successfully create an electric field that causes 4 groups of cells to form. So let's try and find some electric field that will allow for 4 groupings of cells into 4 xenobots.
What's the range of values for that?
There's none.
No, you.
I mean, I would generally keep it between like -2 and 2.
Okay.
Otherwise, you're sort of like, you know, if we go up to 10,000, then we're like really just
Okay.
forcing the system into large values. But there is technically no range, but generally keep it between like -2 and 2. And you can do decimals. You can do like 0.5. Keep in mind that as you increase the number of seconds that this video plays for, it will dramatically increase the time that it takes to execute that cell.
So, this one, oh, I see. Who's the reverse? I'm just breaking them up so we won't change the signs.
You have the answer?
Do I?
Yeah. It's not from. This is from my copy. Wait, on the wrong one? Oh, yeah. I'm sorry.
Yes. Exactly, yeah.
Oh.
And not do it in a way which is, because of course, change it, change the motion. The field of the sausage. Yeah, no, it's beautiful. And this is,
No, that's.
I gotta be What did we say? -1 is why I asked.
Anybody have any luck? It's hard, right?
Wait, what were the minimum and maximum for the E fields?
Generally, technically there is one. I would keep it within -2 to 2.
Okay.
Really -1 to 1, but if you want to go a little bit further.
So, the electric field that you just produced is the solution that would then generate the.
Well,
No.
it's my best attempt at it.
I'm just wondering if there are multiple solutions.
Oh, yeah.
Okay,
Absolutely.
For the same, for the 4 groupings.
Yep, so this is, this that I just flashed up on screen, this is my best attempt at it, but actually, I'll run this and then we'll watch. Where even my best attempt, where, you know, it creates an electric field that kind of looks like it has 1, 2, 3, 4 sort of wells of electrode movement that it might produce. The cells don't necessarily act exactly as you want them to.
Right.
And so it doesn't really, I just by sort of brute force managed to produce an electric field that looks a little right, but we'll see if it has that cell movement that is correct.
Oh, right, of course, because the belongingness. Yeah. You have to, your electric field has to more than compensate for belongingness.
For exact details on the interactions between the cells and our simulated electric field, please feel free to harass Josh when he comes back. He wrote this Git repo. But so this again is my best attempt at a solution, and you see that it kind of doesn't really produce the 4 cells that we want it to. Even, I don't have the video on me right now, but even when we run it out to, 10 seconds, it just takes a lot longer to, it doesn't really. And so this is where the power of simulation really comes to light, because hopefully this has allowed you to experience a little bit the difficulty of finding what the proper intervention is to get the behavior from xenobots we want. And if we were doing this in reality, if we were having Pi or Doug make us, however many the xenobits, the cells, and try and form them into experiments, it's very expensive, but we can do it in simulation, and we can see how they behave in simulation, and then hope later down the line that crosses the reality gap. That's its own difficulty. But even in simulation, it's hard to just brute force it. And so that is really where AI comes in. That is where this will be done by Sean tomorrow. He will walk you through, instead of just simulation, optimization and optimizing this electric field to get the behavior we want of these 4 groupings of cells. Just as a sneak peek, he'll use an evolutionary hill climber in order to do that. But yeah, this is, hopefully you got some feeling for the power of simulation and also the difficulty of just finding something that works the first time or by brute force, because it's hard. Like I said, this on the screen that's right now, this is my best solution in playing with it and fiddling with it for a week, but it's still clearly not the right solution.
No, but
So,
it's
yeah.
great you got the Taurus.
Mm-hmm.
That's
Yeah.
amazing. That is really, that's better than 4 clumps.
True. Yeah, you can get some really interesting behaviors with it. Yeah, feel free to keep playing. Obviously, like I said, this Google Colab that you created is free for everyone. It'll continue to be used tomorrow. You'll see that there's a second section of it that's called Day 2. That'll be with Sean tomorrow. All of the videos that were forcibly just downloaded onto your device, please feel free to delete them. If you want to save them, also feel free to do that. That's fine. But
Can we see your electromagnet?
yeah,
Yeah.
absolutely. So this is
Yeah, that's not what mine looks like.
how to get it both in there. Well, that's my field, but those are the values that'll give you my field.
Okay.
You're just gonna kind of have to squint. Ignoring for a moment the values that are above them. Don't worry about that. Just worry about the values. All right, continue. Feel free to continue playing, but does anyone have any questions? Yep.
How do you extend the video time?
If you go to step 7, there'll be a num seconds in the WCDO.add electric field. Num seconds equals. That correlates to the number of seconds that it'll play for.
Got it.
Again, the longer it is, the longer it'll take to process, and also the larger it'll be on your device. But.
Sorry if I missed this, but why are you trying, is it that you're trying to get it to be like different islands?
Yes, so basically we're trying to find an electric field that groups the cells into 4 xenobots. So this would be a correlatory project would be right now if we want a xenobot we need to get our experts to form the cells into a bot for us. So part of the project we're working on right now is how can we get the cells to self-assemble into a xenobot. And that question is one of the ways we know how to get to the cells to move in a pattern is using electric field. So can we find an electric field that allows the cells to group?
Is there something you can say about which parameters lead to that type of behavior?
Maybe Mike and Pi can, they're the biology experts. Why electric fields influence.
But I mean, even in the simulation.
Oh, even in the simulation?
Yeah.
We are simulating this electric field by adding a force to the cells that we've created in the simulation. There's so part of this simulation is this first command of pip install PyBullet. PyBullet is a very robust simulation software that does things like enables forces to be applied to objects that are in the simulation. So how we got the electric fields to act is by simulating a force that would be applied as a result of the electric field on the cells.
Okay, thank you.
Yeah. That's one of the sort of intricacies of, I mean, Sean will be, Sean actively works with simulation in a way that I don't. Josh mentioned I get AI networks to understand math, but so I don't work with simulation as much, but definitely Sean tomorrow does a lot of work with simulation and making our simulations a lot better. He'll be able to answer a lot of your questions about how he does it, but one of the difficulties with simulation is getting the simulation to act like the real biology does. Again, it'll never be perfect, because, I mean, this goes back into, I guess, complex networks and stuff like that, but it's the old map analogy of if you ever have a map that can perfectly one-to-one replicate a landscape, then it will be the size of the landscape, and then you've just made the landscape again, right? So like a simulation will never be a perfect recreation of biology. To do that, we would have to simulate down to, you know, subatomic particle interactions, and that would require insane amounts of compute. So we sort of, I don't want to say hack, but like, you know, we just have to figure out solutions for how we can simulate what we see in the actual biology better and better. If that's sometimes it's using spring forces instead of just like a linear force between cells for like an attraction repulsion sort of thing. There's a lot of different ways that that is done in simulation. Sean can speak to it so much better than I can, unfortunately, but yeah.
Thank you.
Yeah.
Amanda, how do you think about your relationship to the open source? Some of this public and open to crowdsourcing collaboration. Do you keep some of it back?
Mm-hmm.
What's the theory?
So I personally, not speaking for the lab, am a big fan of open source. We use a lot of open source things. Like I said, the simulation software we use, PyBullet, that's completely open source, and without it, we would have a lot harder of a time doing simulation because we would have to write it ourselves. Our lab generally, once we have published, encourages open source, and we make all of our repos available publicly as open source once we've done the publication. That just, I think, to me speaks to the reproducibility aspect of academia. I think it's very important. Josh agrees with me, so we do make all of that open source. We are not currently under any confidential contracts. Of course, if we were, then we may have to, you know, keep that a secret. But yeah, I'm a big fan of open source. I think it's a very important tool. I think that being very open about how we are doing our simulation, how we're doing our research, what we're doing with our AI is all really important to trust in the community. So yes, as a lab, we provide everything open source as soon as we've gotten that publication through.
So one thing I'll add to that is some of this work is funded by CREL, which is a DoD lab, and they are generally very good about letting us publish stuff eventually, but there is, for those projects, an extra layer of like NatSec review. Like I have a package for information theory that I would like to open source, but I can't until the lawyers at Crowell, who are all on vacation, I guess, have like given me the thumbs up. So
Yeah.
there are extra layers, but yeah, we get
So-
We
Any-
struggle with this too. I'm curious, do you split the bio component from the sort of the modeling sim AI component? Like, or do you draw a through line to all that? How do you handle the complete project?
Yes, so we, at the moment, with my understanding of our contract with Crowell, I guess Mike, correct me if I'm wrong, if you know, anything that has to specifically do with this, the Crowell project, and could be viewed as data for the Crowell project, has to go through their review first, just to make sure it's not classified. It is worth noting that it comes back to us eventually with an okay, because none of it is classified. This is not a classified project.
Yeah.
So it is just that extra step. However, anything that we work on, like this demo that we did today, has this is not code that we are using to actively simulate for the for that BioBots project that we're working on with Krell. And so all of this today is completely open source.
Yeah.
That's where we shared the Drive With You Even More. You can go directly to this GitHub link and see all the code that Josh wrote. And so we do our best to, as quickly and easily as possible, make everything open source that we can. And if we write publications that don't use data that are on like the Krell project, then we can immediately make those open source right after publication. Otherwise, we just have to wait until the lawyers get back to us and say we can.
Yeah, that's great. Thank you.
Yeah, absolutely. Any other questions? I know that Mr. Wolfram is up next. I don't know where he is. Yeah.
Sorry, I just thought of a question. Have you ever done something in simulation and then tried to do it with the actual cells and it's not worked out?
Absolutely.
Yeah.
Yes. The sim to real gap is very real. That's why we are constantly having to improve our simulation. I don't know how much Josh talked about this infinity loop of sim to real to sim today in his presentation. I was unfortunately dealing with another concern during it. But basically, one of our goals with this project we're working on with Krell is to have this feedback loop of like the AI dreams up something, sends it off to an actual robot that does that intervention, records what the robot thinks, sends it back to the AI, and the AI can see if it did what it expected to or not, and then adjust its own internal expectation of like what it thought this intervention would do, and then constantly that infinity loop just goes around and around so that we can get better and better at actually seeing what we want from simulation into reality. So no, we don't always see what happened in simulation in reality, but we're working on getting a lot better at that so that one day we can have this like really powerful model, this really powerful simulation sandbox environment where we can just say like, oh, it's been trained for years now on specifically Xenobot data. It may not apply to anything else if you put a robot made of bird cells, or I think Josh mentioned human cells, you put an Anthrobot in there, it may not behave like this, but we have so much data on Xenobots that we know what this Xenobot is going to do, kind of thing.
Okay, any other questions? All right, thank you so much.
And yes, again, if you have questions about simulations, please feel free to ask.